Imagine two particles separated by vast distances, perhaps one on Earth and the other on the Moon. Yet somehow they are connected. When one particle changes, the other responds instantly, faster than the speed of light. It sounds like something out of science fiction, but this is the reality of quantum entanglement, one of the strangest and most mind-bending phenomena in physics. Today, we're diving into the bizarre world of quantum entanglement to uncover how this phenomenon works and why Einstein himself found it deeply unsettling. So, what exactly is quantum entanglement? To understand it, let's start with the basics of quantum mechanics. Unlike classical physics, where particles behave predictably, quantum mechanics tells us that particles like electrons and photons exist in a state of probability. This means they don't have a defined position or speed until we observe them. But here's where things get even weirder. When two particles become entangled, their states become linked. If we measure one particle, we instantly know the state of the other, no matter how far apart they are. It's as if they're communicating across space in ways that defy everything we know about the universe. But how did we even discover such a strange phenomenon? In the early 20th century, physicists like Albert Einstein, Niels Bohr, and Erwin Schrödinger were developing quantum theory. While they made groundbreaking discoveries, they couldn't agree on what these findings meant. Einstein famously called quantum entanglement spooky action at a distance because he believed that nothing could travel faster than light, not even information. The idea that two particles could instantaneously affect each other seemed impossible to him. But later experiments proved Einstein wrong, showing that entanglement is not only real, but happens faster than the speed of light. So, how does entanglement work? And what does it mean for the world around us? One theory suggests that entangled particles share information through a hidden layer of reality, a concept known as non-locality. This means that while the particles appear separate in our observable world, they are somehow connected in a deeper, invisible way. Imagine them as two dancers perfectly synchronized, moving in harmony even if they can't see each other. It's a phenomenon so counterintuitive that it challenges our very understanding of space and time. Quantum entanglement doesn't just make for interesting theories, it has practical implications as well. In recent years, scientists have begun developing quantum computers, machines that use the principles of entanglement and superposition to perform calculations far beyond the capability of classical computers. These quantum computers could revolutionize everything from cryptography to medicine, solving complex problems in seconds that would take classical computers centuries. Imagine a world where we could simulate molecular interactions in real time, leading to breakthroughs in drug discovery and even unlocking cures for diseases. Quantum computing is no longer just a theoretical dream. It's becoming a reality, and entanglement is at its core. At this point, you might be wondering, if quantum entanglement defies the speed of light, could it be used for faster-than-light communication? The answer, surprisingly, is no. Although entangled particles respond instantaneously, we can't control the outcome of these measurements, which means we can't send specific information between the particles. In other words, while entanglement is a form of instant connection, it doesn't allow for controllable communication. It's like having a twin who feels what you feel, but you can't directly speak to them or tell them what to do. Quantum entanglement also raises profound questions about the nature of reality itself. Some scientists believe that entanglement hints at a holographic universe, the idea that our three-dimensional reality might be an illusion generated by information encoded on a two-dimensional surface. It's a mind-bending concept, suggesting that everything we experience as real might just be a projection. If this theory holds true, entanglement could be the key to understanding how our universe is structured and why particles behave the way they do. The study of quantum entanglement is not just limited to laboratories. In 2017, Chinese scientists successfully conducted an experiment where they entangled photons over a distance of 1,200 kilometers using a satellite named Mikius. This was a major breakthrough in the field of quantum communication and could pave the way for a future of secure, unhackable information transfer. Unlike classical data, which can be intercepted, quantum information is almost impossible to hack because any interference would disrupt the entangled particles. Imagine a future where all of our data, banking, medical, personal, travels securely thanks to quantum entanglement. If all of this sounds a bit like magic, you're not alone. Quantum entanglement is one of the most puzzling and least understood aspects of physics. Scientists have spent decades trying to understand why entanglement occurs and how it fits into our understanding of reality, yet we're still left with more questions than answers. Some physicists believe that understanding entanglement might even require a new form of physics, one that goes beyond the theories of Einstein and quantum mechanics. As we wrap up, quantum entanglement is a reminder of how much we still have to learn about the universe. It's a strange, almost mystical phenomenon that challenges our understanding of reality, space, and time. Whether it's through quantum computers, secure communication, or even deeper theories about the fabric of the universe, entanglement is paving the way for a future we can barely imagine. If you found this dive into the bizarre world of quantum entanglement as mind-blowing as we did, make sure to subscribe for more explorations into the mysteries of the universe. And let us know in the comments, what do you think is the true nature of quantum entanglement? A window into another reality, or just another quirk of physics? We'd love to hear your thoughts.